right, we're going to talk about the Lagrange error bound practice that I handed out in class the other day. And I just wanted to show the actual document here. Hang on. All right, so there we go. I have the Lagrange, additional practice showing. I don't know why it's highlighting the word small, but there we go. I got it deselected. All right, so the first question says, the hyperbolic sine is defined as sinh of x. So that's just a hyperbolic sine e to the x minus e to the negative x over 2. And it's just an exponential function that's a composition of, an exponential growth and an exponential decay. But in many ways, it behaves like a trig function. And that's why it's got the fancy name. But I'm going to rewrite this as 1/2 e to the x minus e to the negative x, because we're going to use the third order Taylor polynomial, which they gave us. They're saying we're going to approximate it using x plus x cubed over 3 factorial. And we're going to use this Taylor polynomial to approximate this function for absolute value of x less than or equal to 2. This is a top secret way of saying that we're going to have our domain for this approximation be limited from -2 to 2. And this is centered at 0, clearly, because my polynomial here is not shifted by any horizontal shift. And so I am going to see how bad my error is going to be in this interval. Well, I have taken the liberty of graphing the sinh function ahead of time. So there it is. And you can see that, it kind of looks like it's a cubic, but it's not really, because it's an exponential combined composition there. But anyway, that's what it looks like. And we're going to approximate it from -2 to 2. All right. Well, Lagrange says if we are going to approximate, get my camera back on here, that the remainder, or the error, for this is third degree, so I'm going to put a 3 here, of x here, the absolute value of it, the magnitude of the error is going to be less than or equal to the next derivative. Here we go, the fourth derivative, evaluated at some c, x minus 0 to the fourth over 4 factorial. Okay, I'll put absolute value because we're just worried about the magnitude of the error here. Now, Lagrange said this function here, this fourth derivative of sinh, is a function in its own right and might have some error consideration that is a maximum. So I like to we use the maximum here of this function in the interval between -2 and 2. So in order to consider that, I need to find the fourth derivative. So f of x is equal to 1/2 e to the x minus e to the negative x, excuse me. And you'll see now why I wrote it this way, because the constant just goes along for the ride. And we have e to the x, and I take the derivative of negative e to the negative x, and that's plus e to the negative x. And then take the derivative again, we get 1/2 e to the x minus e to the negative x. Third time, we get 1/2 e to the x minus e to the, or plus e to the negative x. And then the fourth derivative is 1/2 e to the x minus e to the negative x. And wow, this looks like what we started with. So the fourth derivative of the sinh function is itself. Okay, so I need to find the maximum of this fourth derivative, because that'll be the worst case scenario of the error between -2 and 2. And we remember, if we recall the graph here, that it's going to be clearly at 2. Does everybody see that the biggest value between -2 and 2? And this is an odd function, so it's going to be at -2 or 2, but we may as well take the positive value. It's going to be at 2. Okay, so the max value right here that I'm going to put is going to be at 2. And the error is always worse, as we have often discussed, on the outside of that interval. So I'm going to use 2 as my x, because that's the farthest away from the center, and that's where the error will be the worst. Okay, so I'm going to say that the max error here is going to occur at 2, so x is 2, and I'm going to say that this error will be at least, or less than or equal to, the maximum, which would be e to the second, if I put 2 in here, minus e to the -2 over 2, and then 2 to the 4th over 4 factorial. And knowing that this is the maximum of the fourth derivative between -2 and 2, that's what goes here. And Lagrange said that would be the worst case of your error. And so it would be a nice upper bound. Okay, so if I were to put the numbers in my calculator for that, you can see here, clear out my memory here. All right, I'm going to type in the numerator here, which is e to the second minus e to the -2 divided by 2. I better put parentheses around that. Divided by 2 times 2 to the 4th. And I need to do all that divided by, so I need to set a parentheses over there. Divided by 4. And the factorial button, for those of you who might not know, is diamond divide. Diamond divide. You see the factorial, which is pretty cool. And then we're going to get the number 2 point. So this is less than or equal to 2.418 approximately, right? And so that's going to be in our document, the answer choice E. All right, so let's go over how we did that really quickly. To use the Lagrange form of the error, we figure out that we're using a third degree Taylor polynomial. So I put a 3 here because that's the remainder associated with the third degree Taylor polynomial. And then I'm going to find the fourth derivative and figure out where the maximum is in my interval from the center to where my approximation is. And I find the fourth derivative, which is a function in its own right. I find the maximum over that interval, and in this case we found it was just going to be when x was 2. And then I plug in where I want my worst case approximation, which is at 2, because that's the farthest from the center, which is 0. And I go 2 to the 4th over 4 factorial, because that fills in the formula. And then we figured out that it would be less than or equal to 2.418, which isn't the greatest error, but we're just approximating, and we're very far from the center, so I would expect it to not be a great error, or a great approximation and have lots of error. All right, let's try number 2. Number 2 states, what is the smallest order of Taylor polynomial created at x equal 1, which will approximate e to the x minus 1 on the domain -1 to 3 with the Lagrange error bound less than 1? Now, that's a lot of words. Okay, so what is the Taylor polynomial for e to the x minus 1 centered at x equal 1? Well, I got to do a little bit of work here. So we're going to go f of x equals e to the x minus 1. F prime of x is equal to e to the x minus 1 because the derivative of this exponent is 1. So we were very lucky to get a function like this. The second derivative is equal to e to the x minus 1. The third derivative, again, is e to the x minus 1. The fourth derivative is e to the x minus 1. And the fifth derivative is e to the x minus 1. And if we were going to do the sixth derivative just to see if we might need that, now I've done the problem ahead of time so that I could be as good as I could be on this video. But anyway, we're centered at 1, so I need to evaluate my function at 1. So I'm thinking we're going to need one of these degrees. So what happens when I plug in 1 into all of these functions? Well, I just get e to the 0, which is 1. So all of these evaluated at 1 are equal to 1, which is really nice. Can I write today? I hope so. All right, the fourth derivative evaluated at 1 is 1. The fifth derivative evaluated at 1 is 1. The sixth derivative evaluated at 1 is 1. All right, so my polynomial is going to be, well, remember it's f of 1 over 1 factorial, which is 1, plus f prime of 1 over 1 factorial. I'm sorry, this is f prime of 1 over 0 factorial is the first one, plus f prime of 1 over 1 factorial times x minus 1 because we're centered at 1, plus f double prime of 1 over 2 factorial, which is 1 over 2 factorial. So this is just x minus 1 squared over 2 factorial. And I'm sure you're starting to see the pattern, or should see the pattern here, that it's going to be this. Over 4 factorial plus x minus 1 to the 5th over 5 factorial plus x minus 1 to the 6th over 6 factorial plus dot, dot, dot. If I were going to put the next term, it would be x minus 1 to the n over n factorial plus dot, dot, dot. All right. So I don't know what degree is going to be the smallest that'll give me an error bound of less than 1. So let's figure out what it would be if it was just n, if I used the nth term. So it would be error using an n degree polynomial. It has to be less than or equal to the nth derivative plus 1 evaluated somewhere that'll give me a maximum times x minus 1, because that's the center, to the n plus 1 divided by n plus 1 factorial. Okay? Now, if we think about what this function is, on any of the derivatives here, it's e to the negative 1, e to the x minus 1. And that function, if we look at it, we analyze it really quickly, it's the e to the x function shifted to the right by 1, so it's going to be shifted to the right by 1. And the interval that our problem is stating we have to consider is, it says the domain from negative 1 to 3. So from negative 1 to 3, I'm going to have a maximum somewhere on this function. And I hope everybody sees that it's clearly going to be when x is 3. Okay, so when x is 3, my function value is going to be, no matter what the derivative, it's going to be e to the 3 minus 1, or e squared. So the value that I'm going to put here for no matter what the derivative is e squared. And then how far am I going to be away from the interval here on either side? I mean, from the center on either side. Well, that's going to be 2. So the worst case for the error is going to be 2 away. So this is going to be 2 to the n plus 1 over n plus 1 factorial, because I don't know what n is, because I want to find out when the error will be less than 1. So I'm trying to find out when this expression is going to be less than 1. All right, now I've got some options here. I could do a chart where I put n here and I put e squared 2 to the n plus 1 over n plus 1, and I actually physically do the calculations. All right, because we could say n is 1, n is 2, n is 3, n is 4, 5, and then, oops, you can't see it. I'm sorry, I get it on the screen. N is 6, because that's how many I have. And I could go further. It wouldn't be that hard to go further, because this nth term applies to whatever the degree is. All right, so I'm getting my calculator out here, and I'm going to clear out that home page there. All right, so I'm going to type in my expression, which is parentheses e to the second times 2 raised to the parentheses. I'm going to put x plus 1 divided by, now that's the numerator, so divided by parentheses x plus 1 close parentheses diamond divide, because that's factorial. All right, and there we go. Well, I don't need to see this, but okay. But I'm going to do such that x equals 1. Oh, wait, this is a minus sign, so I don't need that to be minus. Silly girl. All right, you guys were probably screaming at me from behind saying, oh no, Mrs. Muller, you can't do that. Okay. There we go, I like that better. So that's 2e squared, which is approximately, wow, 14.778. That's a lot of error. So the first degree, let's not use that one. And it's certainly not less than 1. But what I like about this setup is that I've got the such that bar, so I can just go back and change the last number every time. So I can go 2 here. Well, and then let's do the approximate. And then we get 9.852. 9.852. And then we can go to the end, make it 3. I'm going to approximate, and that's 4.926. We're getting closer to 1 with this a third degree. So let's see what happens when I put this as 4. We get 1.970. And now let's make it degree 5. Ooh, 6, 5, 6, 8. 6, 5, 6, 8. Now remember, the AP folks would let you truncate this. So you could say 0.656 or you could say 0.657. So either one they would accept. All right, well, guess what? This is the first one that is less than 1. And the question said, what's the smallest order? Well, the smallest order is going to be 5. Now, I'm going to just do 6 for kicks and giggles here. So I'm going to do 6 here. And is the error less than 1 there? Well, yeah, clearly it is, right? Because we get 0.187. 0.18765. Okay, so this is also less than 1. And I had a question stating, well, if 6 is less than 1, sure, 7 is going to be less than 1. All the ones after 5, 5 and later, are going to be less than 1. But the question asked for the smallest order or the smallest degree. So we can say the smallest order or degree Taylor polynomial for e to the x minus 1 for error, for not the exact error, but for the Lagrange part of the error. For the Lagrange error to be less than 1 is 5. And this is our proof here. which is pretty clear. And we could also, I think, graph the function. Now I'm going to go to the home screen here. I'm going to see if this works. I didn't try this ahead of time, which, when I do that, we get in trouble. But I'm going to go diamond copy because we can do that. And I'm going to go diamond y equals and go enter diamond paste. I'm going to get rid of the x equals 6. And so this right here is the term I'm looking for my error. Sorry about the little dot here, but okay. And let's see what that graph looks like. Well, I don't know what my window is yet. I'm going to break this and change my window. Let's change my window from negative, because I want to be from -1 to 3. So let's make it -5 to 5 in the x direction. And we had error as bad as, goodness, is 14 here. So I'm going to make my y's at least, I'll make it -3 because I like to see the x-axis. To, well, 18 works, I think. And we'll make our y scale in 1, and x scale 1 here. All right, diamond graph. Let's see what happens. Oops. Let's see, diamond window. What did I do? Haha, I got to make it -5. That helps. All right, so what am I graphing? I'm graphing the Lagrange error. If it will graph. Ooh, we don't see it at all, do we? That's a bummer. I wonder why it's not graphing. Maybe it doesn't like the factorial in there. All right, I'm going to play around here. Let's see if it'll graph x factorial, which might be the problem. I don't know. No, it doesn't like to graph factorials. Good to know. All right, well, we discovered something together. But maybe Desmos will let us graph it. So let's play and see if Desmos will let us graph it. So let's say we have y equals, what did we say our function was? Yep, we said our function was a fraction, which was e raised to the second times, whoops, 2 raised to the x plus 1, close, and hop down to the denominator and say x plus 1 close factorial. Ooh. Wow. Okay. Well, at least it's letting us graph it. That's nice. That's the, we want to know when it's less than 1, don't we? Oops, sorry. So we want to know when this function is less than 1. So I'm going to put y equals 1 on here. All right. Well, it's 4.6 something, right? Which means I can't have a 4.635 degree Taylor polynomial. We have to have integer exponents. So it's going to have to be a minimum of 5, because you see how when I put, I'll label this f of x. Okay, and then I'll say I want f of, we'll make a point and we'll say 5 comma f of 5 and put a label. And you see where we get the 0.657 right here, which is what we got on our error for when we used the 5th degree polynomial. So we got this function. It will equal 4 point something when it equals 1, but we can't have a 4 point something degree Taylor polynomial. So the smallest one we'll have is 5. So that was kind of a cool experiment. We learned how to do cant graph with factorial on 89, or at least not that I know of at the moment, which will be a discussion for another time. All right, let's try number 3. Moving along. Number 3. Looking at the document, number 3 states the approximation for natural log of 1 plus x is using x minus x squared over 2. So they're telling us we're going to use a Taylor polynomial degree 2 for this approximation. It's going to be x minus x squared over 2. And it's used when x is small. So use the remainder estimation theorem, which is another way, or another all right, sorry about that. My puppy had to go outside. That's what she was telling me, and I needed to listen because she's a great puppy and deserves to be listened to. So, especially when she wants to go to the bathroom. All right, I'm sorry. So we were on number 3, where we're going to approximate the natural log of 1 plus x approximately with a Taylor polynomial degree 2, which they gave us. And I'm sorry, on the screen, I recall it was going to be for small values of x. And it looks as though they are giving us another range, and that's going to be between, for x's absolute value, between or less than or equal to 0.1, which means we're going to be looking between 0.1 and negative 0.1 and 0.1. And so if I'm going to use the remainder estimation theorem, which happens to be Lagrange, that's the same name, the same theorem, different, same, Lagrange came up with it. That's why they affectionately call it Lagrange. So we're going to use the same thing, but we have a second degree Taylor polynomial here, so we're going to have to use the third derivative for this to calculate the term, for the approximation for the error. So here we go. I have to say f of x is equal to the natural log of 1 plus x. F prime of x is equal to 1 over 1 plus x, because it's f prime over x for the derivative of the natural log. And that equals 1 plus x to the negative 1 for ease of taking a derivative. So let's take the second derivative, which would be negative 1 plus x to the negative 2. And then the third derivative, which is one we need, is going to be 2 times 1 plus x to the negative 3, which is 2 over 1 plus x quantity cubed. And I know that the remainder of x, the approximation for the remainder, is going to be less than or equal to the third derivative evaluated somewhere that's going to be a maximum in this zone. And this is centered again at 0 because I don't have any shift in my polynomial, so it's going to be x minus 0 to the third over 3 factorial. And knowing that this is going to be a maximum that we find on the third derivative function between here and here, we need to think about what this function looks like. Well, it's a rational function, and it's got a vertical asymptote at negative 1. And if I put 0 in for x, I get 2. So up here we got a 2. And then we have got a horizontal asymptote at 0. And clearly this function is going to look like this in this zone on the left side or the right side of x equals negative 1, because I'm looking in the negative 0.1 to 0.1 realm. So where's the maximum of this function going to be? Well, this function is going to have a maximum at, it looks like, negative 0.1. So that's the number that's going to go here. So what is the number? Well, I need f triple prime evaluated at negative 0.1. And that's going to be 2 over 0.9 cubed. So that's the number that's going to go there. 2 over 0.9 cubed times, well, where's the worst case scenario for the error? So when you're farthest away from the center, which is going to be at 1 or 0.1 or negative 0.1. And so we can say negative 0.1 cubed over 3 factorial. Since it's absolute value, I don't have to worry about this 0.1. And so we can say it's going to be 2 over, I think that's 0.729 times 0.001 over 3 factorial. And this would be good enough right here for a non-calculator section. And if we wanted to figure out what that number was, we would put that in the calculator. And let's clear out my home screen, F18. And then I'm going to put in the original number, which is 2 divided by, let's put parentheses around it, 0.9 raised to the third times 0.1 raised to the third divided by 3 diamond divide. And that's our error. I hope everybody can see that, right? That's going to be less than or equal to 4.572 times 10 to the negative fourth, or if we put it in a decimal, 0.000457. Okay, so that's the Lagrange error bound. That's the upper bound of the error if I use only these two terms. Okay, so is that accurate? Well, what would the actual error be? Well, you would take this function evaluated at 0.1 or negative 0.1 and see what the difference is. And this is pretty good, actually. All right, let's do number 4. The approximation of e to the x we're going to use here in this problem is 1 plus x squared over 2. And we're going to use that approximation when x is small. Use the remainder theorem to estimate the error when we are in the realm of absolute value of x less than or equal to 0.1 again, which means our error is going to lie between 0.1 and negative 0.1. So in this case, again, we're using a second degree Taylor polynomial to estimate or approximate a function. And I'm going to use the remainder estimation theorem or the Lagrange error bound. So I need the third degree. So we say f of x equals e to the x, f prime of x equals e to the x, f double prime of x equals e to the x, and f triple prime of x equals e to the x. And I know that e to the x, and I know you know e to the x looks like this, but in the realm from negative 0.1 to 0.1, the maximum is going to be e to the 0.1, looks like on this zone. All right, so we're going to find the second derivative. I mean the remainder using the second degree of Taylor polynomial. That's why those twos match. It's going to be less than or equal to the absolute value of the third derivative evaluated at some location, which is the max. And this is also centered at 0, x minus 0 raised to the third over 3 factorial. And so what is the max in this case? Well, we see that the max over the interval from negative 0.1 to 0.1 is going to be e to the 0.1. And then we would say times 0.1 to the third over 3 factorial. And you see, these problems get easier and easier the more that you do, or you don't even have to do that many. All right, so let's put this in the calculator. So we're going to get, clear this out, parentheses, diamond e to the 0.1 times 0.1 raised to the third, close the numerator, divided by 3, diamond divide is factorial, and we're going to get, what is that, 1.842? Less than or equal to 1.842 times 10 to the negative 4. So that error is going to be 0.000184. Using only the second degree Taylor polynomial for small x. So we're close to our center. So that's what the upper bound of the error is. Meaning the error, this is the worst case scenario. It's going to be better than this. And that's why Lagrange came up with this method. So we're going to use the worst case scenario, and we know our error will be better than that. All right, so hopefully you're getting the hang of it. Let's do number 5. And then be done with this lovely video for Saturday. All right, number 5, which is kind of a nice summary problem. Number 5 states, let f of x equal a power series. How do I know it's a power series? Because it's got an x in my nth term. So this is n equals 1 to infinity of x to the n to the n, divided by n factorial. Okay? And this says this is equal to f of x for all x for which the series converges. So this only works on its interval of convergence. All right, so part A says to find the radius of convergence. So we're going to say using the ratio test. Here we go. Using the ratio test, that means we're going to take the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n, which means I'm going to take the limit as n goes to infinity of the absolute value of x to the n plus 1 times n plus 1 raised to the n plus 1 over n plus 1 factorial divided by, long graphs with value bars, x to the n, n to the n over n factorial. And then I'm going to do the algebra there where I reciprocate the denominator here when I'm dividing. So this is the limit as n goes to infinity of the absolute value of x to the n plus 1 times n plus 1 to the n plus 1 over n plus 1 factorial times n factorial over x to the n to the n. All right, and then we're going to simplify a bit. Life happens in the background. All right, I'm going to simplify a bit, which x to the n plus 1 over x to the n is just x to the first. And then we know that we have inside the n plus 1 factorial is an n factorial waiting to be canceled out. So this is n plus 1 times n factorial, which I can cancel out. So I'm left with just n plus 1 in the denominator here, times an n plus 1, and I'm going to bust this up. This is n plus 1 to the n plus 1. So I'm going to say this is n plus 1 to the n times n plus 1 divided by the last one here, which is n to the n. Now why I did this is because I can split this up. I have the same base, and this really is to the first. So when you multiply two things with the same base, you add the exponent. So this would be n plus 1 to the n plus 1. You see, I haven't really changed. I just changed the way it looked. And now I see that I have these two things both raised to the n, and I can cancel out the n plus 1. Okay, I know it's fancy, but it works. So the limit then, as n goes to infinity, of the absolute value of, then I have x times n plus 1 over n raised to the n. And this is a special limit, and I'm going to rewrite it so you can see what I mean. This is the limit as n goes to infinity of the absolute value of x times 1 plus 1 over n to the n. And I've been saying this for since folks are in pre-cal, that this is a limit that we need to know how to do, or know that its value, okay? And its value, believe it or not, if you guys did L'Hopital's rule and figured it out, this value here, this limit as n goes to infinity, is e. So this limit's actually equal to, when n goes to infinity, x is a constant, and so we get e, absolute value of ex. And so then this series will converge when the absolute value of ex is less than 1, which means ex has to lie between -1 and 1. Dividing everything by e, I get -1 over e. Is less than x, it's less than 1 over e. So using my tie-interceptor, we get a center of 0, and my radius of convergence here, r, is equal to 1 over e. And the IOC, or the interval of convergence, is -1 over e, comma 1 over e. You can't see what I wrote there, but there it is. And in a later discussion on a video, we would check the endpoints here to see if they converge at the endpoints, but that's not what we're going to do here for part A. Okay, so for part A, the answer is the radius of convergence is 1 over e. Well, good. Now we're on to part B. And it says, use the first three terms of this series to approximate f of -1/3. Okay, so our this is for part B. So our sum is from n equals 1 to infinity of x to the n to the n, divided by n factorial. And I'm going to need the first three terms. So I'm going to expand this, and expanding this, I get what happens when I plug in n equal 1. I get x to the first, and n equals 1, so it's going to be just 1, plus if I let n equal 2, I get x squared times 2 squared over 2 factorial, plus the third term would be x cubed times 3 to the third over 3 factorial. It doesn't look like very pretty writing there, so I'll fix that. So it'll be 3 to the third over 3 factorial, plus so on, right? We can keep going. And so we're going to approximate f of x using the first three terms. So there we go, 1 plus, this is going to be 4 over 2, so that would be 2x squared plus, and then I get 27 over 6, which is 9 halves, quickly in my head, x cubed. All right. So I need to approximate f of -1/3 using those three terms. So this is going to be 1 plus 2 times -1/3 squared plus 9 halves times -1/3 cubed. So that's 1 plus 2 ninths. Oh wait, I'm sorry. This you should roll back the tape. There, I rolled back the tape. Did you hear it? This is x. So this is x, and this is -1/3. -1/3. See, I had that little haunting feeling that I had. When n is 1, this is x. Silly girl I was. Okay, well, I remedied it. A minute in, but I remedied it. Okay, so this is -1/3 plus 2 ninths plus, or minus, that's going to be 9 over 6. No, 9 over 2 times 27. Negative 1/3 plus 2/9 minus, this goes away, this goes to 3, negative 1/6, which I can write all in 18ths, which will be negative 6 over 18 plus 4 over 18 minus 3 over 18, which is negative 9 plus 4, which is negative 5 over 18. Whoop, negative 5 over 18. So I can say f of negative 1/3 is approximately, using the third degree Taylor polynomial, negative 5 over 18. Oops. So thank goodness I went back and fixed that. All right. Try for perfection, but you know, we're only human. All right, so part C says estimate the error involved in the approximation for part B. Well, I don't have a function for this, right? So I can't take its derivative however many times, the four times to get the fourth term, to do the Lagrange form of the error. So I'm going to have to try something else. So I'm going to use the first discarded term to approximate my error. Okay, so I'm going to say the error, the magnitude of the error is approximately, well, what happens when I have the next discarded term? That's going to be x to the fourth times 4 to the fourth over 4 factorial, such that we're going to let x equal negative 1/3, right? Because that's where our approximation is. So that's going to be 1/4, or negative 1/3 to the fourth, and this is going to be absolute value here, but this will be 3 to the fourth is 81. So this is 1 over 81 times 4 to the fourth, which is really going to be 4 to the third over 3 factorial, because one of the fours will cancel, right? Which is going to be equal to 1 over 81 times 64 over 6. 64 over 6. If I divide 2 into both of these, I get 32, and I get 3. So 81 times 3, so it's 32 over, you can't see my calculations, sorry, 243 is my error approximation using the first discarded term. You know, and this problem didn't state I had to use Lagrange either, so I could use the first discarded term, which is pretty cool, because you have a choice sometimes, even though you might not believe you have a choice sometimes. But all right, then summary, that is my working through the Lagrange error bound additional practice worksheet, which I promised to do. So you guys have a great rest of your morning, afternoon, or evening, whatever the case may be, and I will chat with you next time.